Today we're going to do section 9.4, comparison of series. So let's look at this warm-up. We learned that the harmonic series diverges. Is the last example close enough to the harmonic series so that we can compare and determine if f of x diverges? So this was the last example from section 9.3. We looked at 1 over n natural log of n, and the series diverged by the integral test. Okay, and we want to know, can we show that, compare, and determine if something converges? And it's not going to work here, and this is why. For every term for the second series is smaller than the harmonic series. Just because the larger series diverges does not tell us whether the smaller series diverges. Let's look at theorem 9.13, limit comparison test. Suppose that an is less than 0 and bn is less than 0, and the limit of an over bn as n approaches infinity equals L, where L is finite and positive. Then the series an and the series bn either both converge or both diverge. If you get 0, you cannot use this. So let's look at example 1, the limit comparison test. Determine the convergence or divergence of a series. So here, we need to compare this one to something else. So we need to compare this to the simplified form. So usually when I'm looking at something to compare this, I look at these two here. Okay? And we want to compare to this simplified term. The plus 1 is insignificant because that's just adding a constant. Okay? So we want to compare this to 1 over n to the 3 halves because that would be the simplified form of the square root of n over n squared. Okay? So we would take the limit as n approaches infinity of the square root of n all over n squared plus 1, all divided by 1 over n to the 3 halves. And n to the 3 halves, we know, is a p series. So keep that in mind. And when we go ahead and do this, we would get the limit as n approaches infinity of, you multiply by the reciprocal, and you end up getting n squared over n squared plus 1, which equals 1. Okay? So we know that from n equals 1 to infinity, 1 over n to the 3 halves converges by the p-series test. Where p equals 3 halves is greater than 1. Okay? Therefore, our original series converges by the limit comparison test. Because you get something finite and positive. So that limit here was finite and positive. It was 1. So let's look at the second example. We're going to look at the series from n equals 1 to infinity of n times 2 to the n all over 4 n cubed plus 1. So we're going to compare this to the simplified form here. So if I look at this, I would compare it to this, but we don't need to have the coefficient of 4. The n's cancel out, so we're going to compare it to 2 to the n over n squared. So first we want to see if we get something finite and positive, so we'd have the limit as n approaches infinity of n over, or n times 2 to the n over 4n cubed plus 1, all divided by 2 to the n over n squared. This would be the limit as n approaches infinity of n cubed over 4n cubed plus 1, which equals 1/4. So we get something finite and positive. And we also should know that the limit as n approaches infinity of 2 to the n over n squared equals infinity, which does not equal 0. So by the nth term test, we know that this diverges. And remember, exponentials grow faster than polynomials. Therefore, our series diverges by the limit comparison test. So let's look at theorem 9.12, direct comparison test. So for let 0 be less than an, which is less than or equal to bn for all n, if my series of bn from n equals 1 to infinity converges, then my series for an will also converge. If my series an diverges, then my series bn diverges. If the larger series converges, then the smaller series converges. If the smaller series diverges, then the larger series diverges. So this is kind of like the squeeze theorem. You want to compare these in the correct order. And you want to pick something to compare them to. Have the inequality in the correct order and pick something that you know diverges or converges to compare it to. So let's look at example 2 using the direct comparison test. Determine the convergence or divergence of the series. So here we have the series 1 over 2 plus 3 to the n from n equals 1 to infinity. So we need to compare this to something. So what I look at here, I would compare it to 1 over 3 to the n. Okay, you need to show the comparison. And we know that 1 over 3 to the n would be greater than our series. So 1 over 2 plus 3 to the n is less than or equal to 1 over 3 to the n. We need to show this, and it will diverge. If diverges, it has to be smaller, but here it's larger. Okay, so we need to look at converges. Okay, and we know that 1 over 3 to the n is geometric, and we know that of 1 over 3 to the n converges to 1/2 because it's a geometric series, 1 over 3 all to the n. Okay, so also converges. So our series also converges by direct comparison test. With the limit comparison test, you don't need to worry about which one is bigger or smaller. But with the direct comparison test, you do. Let's look at our second example. So we have 1 over 2 plus the square root of n. So what we would look at here is 1 over the square root of n. Okay, but what I definitely know is 1 over n. I know it's a divergent p-series, and we know that that is smaller than what we have here. Okay, so I'm going to compare 1 over 2 plus the square root of n, and we know that's less than or greater than or equal to 1 over n, because I know 1 over n is a divergent p-series. Okay, my inequality is correct. So since 1 over n is less than my series here, I know it diverges. And it diverges by the direct comparison test. Let's consider the following series. Okay, so we want to see if these converge or diverge. And right now, looking at this, doing our other examples, we would say that we would compare this to 1 over 2 to the n, but we can't because the inequality would be false. Okay, so what we're going to do is we're going to manipulate our inequality for this one. Okay, we're just going to start with 2 to the n is greater than n cubed. Okay, because hopefully we can get a p-series here. Okay, now if I take the reciprocal of both of these, it will look more like this. I would have 1 over 2 to the n is less than 1 over n cubed. So when you take the reciprocal, you have to flip that sign. Okay, now what I can do is I can multiply both sides by n and it will be equivalent. So I can go over here and I would have n over 2 to the n is less than n over n cubed, which actually equals 1 over n squared. And we know that 1 over n squared is a convergent p-series. And by the direct comparison test, because our inequality is correct, our series also converges. So now let's look at our second one. We have the series 1 over n cubed plus 1. So if I have 1 over n cubed plus 1, I can compare this to a p-series 1 over n cubed. We know that the first one will always be smaller or equal to because you have that plus 1. And we know that 1 over n cubed is a convergent p-series because p is greater than 1. And since that one is larger than the one we're comparing it to, by direct comparison test, our series also converges. And now let's look at the last one. If I look to see here, and there should be on your notes an exponent of 4. But if I look here, or an exponent of 2, excuse me. So if I look here and I just ignore that plus 2 for a moment, I would have n squared squared, which would be n to the 4th. And n squared over n to the 4th, I can compare it to n squared, right? So 1 over n squared is definitely larger than everything that I have here in the denominator. So we would know that n squared over n squared plus 2 all squared is definitely smaller than 1 over n squared, because this would be the larger one here. And if my larger one converges, which it does because it's a convergent p-series, my smaller one will converge. So we know that is a convergent p-series because p equals 2, which is greater than 1. So by my direct comparison test, also converges. And the thing with direct comparison tests, you need to make sure that inequality is true for these to all be true. So let's look at the quick quiz for section 9.4. So take a moment. Which of the following series converge? So you have 3 different series here. Either 1 can converge, only 2 converge, only 3, or 2 and 3 and 1 and 2. So go ahead, take a minute, try to figure out which ones converge first, and then choose your answer. And your correct answer should have been E. If you have questions about why the correct answer is E, where only 1 and 2 converge, go ahead and ask that in class.